So first disclaimer, these are the notes on Tuesday's page. You may want to have them out. They're all filled in. So as we go over this right now, I don't really want you trying to recreate what you see up here because there's going to be lots of words. I give it to you filled in with all the math and everything so that we can talk about it, okay? So the first thing we are going to go over is a little bit of review. Different types of answers from a quadratic, because this is where our complex solutions are going to lie. They're going to lie in this quadratic. So you solved a quadratic way back. You got to think back into math 2. Bunch of different ways. But one that we just used in that focus was a quadratic equation. And this was the one that when I taught math 2 many years ago, I referred to. This was the sledgehammer of factoring. May not be pretty, may make a mess sometimes, but it's gonna work. It always works, okay? You wanna get through the door, I guarantee you eventually get there with a sledgehammer, right? It'd probably be better to pick the lock or use the key, a little bit nicer, but sometimes you just gotta beat the door down. And that's really what this does for us. Because some of our more interesting answers, our more messy looking answers, come from looking at it in this format, okay? Now, what happened with this? This thing's got a radical in it, which is a square root sign. It only has real solutions when the stuff underneath is positive, meaning this is the one that could give you, use that determinant to determine if there are three different ways the answers could lie in your quadratic. If it was positive, meaning we got a real number, positive number underneath the square root, like 16. What's the square root of 16? Square root of 16 is 4. We got nice, easy numbers under there. We could finish the addition and subtraction and division to go from there. What happened if we got 0 under that? What's the square root of 0? Anybody remember what the square root of 0 is? It's 0. But when you got 0 underneath that thing, it still gave you a real answer. It gave you 0, but what happened is for our quadratics, we ended up having only one solution for the x-intercept. That was the parabola that just bounced off the x-axis. We say the word bounce now because we kind of have a little bit more understanding of that. But what also happened with this is we could get a negative under that. The math could give us a negative underneath that square root. And way back in math 2, when you learn to deal with this, this is where that number I that we talked about in the beginning of the year came from. If you have a negative under this square root, that's that square root of -1, which we denoted as I, the imaginary unit, and we could get complex answers for this quadratic. So what happens here is when we go through and we're actually factoring, this b squared minus 4ac of our quadratic determines what type of answers we're going to get out of it. If it's positive, you get 2 real answers. That's the most common one that we've dealt with. If we get 0, that was where we ended up with 1, which isn't as important for what we're talking about. This is where we're going to spend our time today, where we do this quadratic factoring with the quadratic equation, and that b squared minus 4ac ends up being negative. Then we still get 2 answers for this thing, but this is where that imaginary or complex solution comes from. So what I want to look at with these, and I don't even necessarily want to find them, I want to determine with this quadratic what type and how many answers I'm going to get, okay? And that all resides in, we're going to pretend that we can't factor this a times c even if we could. We're going to have to plug this into the quadratic formula. What's going to happen underneath this square root determines whether are we going to get a complex solution or a real solution. So let's look at this just in here, this b squared. So b squared is 6 squared, that's 36, right? Minus 4 times 5 times 5. this number, whatever comes out in here, this is the number that's underneath the square root. This will help determine what type of solution I'm going to get. So that's 36 minus 100. What type of number is that? That's going to be negative. So that means we're going to get a negative under the square root, meaning that we're going to have complex solutions for this quadratic. I think I have imaginary. Meaning that it's not, it still has them, it'll still factor. It'll look like those irrational ones did, except we'll have an I in there. If we do that with this one, we end up right here. We end up with 10 squared minus 4 times 5 times 5. Which is 100 minus 100, which gives us 0. That tells us it has one real rule. That one's not quite as important for our process, but I did want to still wanted to include it so that we saw it. Because this is the one that we're looking for. But then this last one, we plugged in and we figured this out. We get 49 minus 24, which is a positive 35. I'm sorry, positive 25. Ooh. Positive 25 has a square root that's real, meaning that this one will give us 2 real roots, okay? This is something that I think as we've gone over it, you may remember. This is from way, way back in Math 2. This feature and this theorem, this fact, is what tells us that our big polynomials, when we get down to our quadratics, it's possible for them to have complex solutions, okay? So as we move forward in finding these roots of this polynomial, this concept will become important again. Because we're going to end up with quadratics that we can't factor, like we saw in that focus, and we're going to end up with quadratics that don't have real solutions. They have complex solutions, and we're going to need to write that factor out, okay? So let's talk about 2 theorems, and then I'm going to actually show you how this works, okay? So one theorem that we're working here is called the fundamental theorem of algebra, which is a very, very big, overarching, broad theorem. The best description I can give you to why this is important is that tool algebra that we use, that you probably used since 6th grade to solve just about everything. This theorem is the reason it works. It's what proves that you can do it, okay? Which is why we spend the time to go through it. But what this says is any polynomial, now this is a polynomial like we defined before, coefficients, variables with powers, with complex coefficients has at least one complex 0. Have we ever seen a polynomial with a complex coefficient? Well, let's talk about complex numbers again because it's been a little while because we did those first. Complex numbers. 3 plus 2i. That's a complex number because it has a real part and a imaginary part. So this is complex. Is 3i complex? Yes, but it's also what? More commonly referred to as imaginary, right? But it's complex because we can put a real part in here. The real part is 0. Now, the one that was more telling, and I had you guys practice this a few times when we worked through it. Let's talk about 16. That's a real number, right? That's the numbers that we've always worked with. But the numbers that we've always worked with are also complex numbers. Because we could put the 0i there. All numbers can be represented as complex numbers. And that's why this theorem right here makes sense. Because every number we've dealt with that we've classified as real is also complex. So therefore, that means every polynomial has at least one complex 0 because all zeros are complex, meaning that you think back to when we found our zeros. If we had x equals 3 was a 0, is that a complex 0? Yes, because there's a 0i with it. I could write its factor like that, but would you ever include the 0? No, because 0 doesn't do anything. So technically we've been working like this forever with all these things that we've ever factored and never done. But we've just never written it down. So what I have right here just written down is it says, because any real number is also a complex number, this theorem applies to polynomials with real coefficients as well. Fundamental theorem of algebra and the factor theorem together show us that any polynomial can be completely factored into linear terms, every single one of them. And what it guarantees is every single polynomial will always have the same number of linear factors as its degree, every time, guaranteed. So complete factorization theorem states that you're going to have as many factors as you do degrees. So if we look at this first example, x to the 6 minus 64, and I want to factor this completely, how many linear factors is it going to have? It's going to have 6 of them, okay? Now this one uses a special formula to factor it first, because I'm not going to go through the whole P over Q list on this one to start with this, okay? I want to get down to the quadratics a little bit faster. So this polynomial off the bat, let me delete all this, factors into this. And it's a formula that you probably don't remember from back in Math 3. But what I'm stating here is that this is the difference of squares. We learned this usually doing this. If I wanted to quickly factor this, I could take the square root of x squared and the square root of 4, and there was a subtraction sign between them. Square root of x squared is x, square root of 4 is 2, so therefore this will factor into x minus 2, x plus 2. And it was a shortcut. We also said that you could factor, and we knew it worked because if we put the 0 in there and drew the box, we would end up with the same answer. But the reason we learn this more like a formula is because this can be expanded. Meaning I could also factor that the same way. That is also the difference of two squares, because I can take the square root of x to the 4th and the square root of 16 and get whole number answers. The square root of x to the 4th is x squared. The square root of 16 is 4. So that means it's one of those things subtracted, one of those things added. You multiply that back out, it'll take you back to the x squared minus 16. The reason we spend a little bit of time with this in Math 3 is these formulas can be expanded to bigger powers, which makes them useful for factoring polynomials. I promise you I'll throw some videos and we'll do some practice with those two formulas to come, but I don't want you to be super confused about where I get this from. The square root of x to the 6th is x to the 3rd, and the square root of 64 is 8. Because now we have to remember the other formula that we work with. And I have them written on the backboard. They are right behind Connor and Kevin. In the middle where it says factoring, there's ones on the left with cubes on them. There's one on the right with the a squared minus b squared stuff. And I'd venture, because a lot of you guys had second semester Math 3, you might not remember this, but we did this like second week of school, which is really makes it even tougher. We will review those, but I wanted to talk about them because I'm factoring them this way because I'm not drawing P over Q and going through the list. I'm trying to go a little faster. So what this is this is the difference of two cubes. And I promise you that it factors into that. This is the sum of two cubes because you can take the cubed root of both of them. And this factors into those two. So the factoring right here, we'll come back to, okay? I promise. But what I want you to get at is, at this point, x to the 6th minus 64 factors into x minus 2 times x squared plus 2x plus 4 times x plus 2 times x squared minus 2x plus 4. So I'm looking for 6 roots. I've already found 2 of them. The first one is right here. That tells me that this graph is going to cross at the x equals 2 mark. This one that says the graph is going to cross at the x equals negative 2. But what about these? These are quadratic, so they should have 2 more roots apiece. So this is starting to make sense. This is going to have 2 solutions, and this is going to have 2 solutions. 2 plus 2 plus 1 plus 1 gives me the 6 that I'm looking for. But if I go to factor this, are there factors of 4 that add together to give me 2? No. So that means that I can't factor this with a times c. It means I'm going to have to use the quadratic formula to factor this. And even more, if you do what we did right here, and you look at what b squared minus 4ac is, 2 squared is 4, minus 4 times 4 times 1. So 4 minus 16, is that a positive number or a negative number? Going to be a negative number, meaning that when we use the quadratic formula on this one, we're going to end up with a complex root. So we're going to factor these things using the quadratic formula. And if I plug into that, I get this. I'm going to start with this one on the left. So this is still the same process. I'm still factoring a polynomial, and I'm going down to my quadratic to use my tools to factor a quadratic. And I get right here, and what I see, that I get that. And then the alarm goes off, because we know that that negative can't be inside that square root. So what do we do with it? So let's write that down and see what we do. We have negative 2 plus or minus the square root of negative 12 over 2. So we need to deal with this square root of negative 12. So we know how to deal with the negative because we know that that's negative 1. But we also, in that same breath, we need to deal with, are there any perfect squares as factors of 12? That's 4 times 3. So that means this is the square root of negative 1 times the square root of 4 times the square root of 3. And these two things have square roots that we know how to write. This is I. This is 2. Nothing changes with that one. So that means this on the top is plus or minus 2 I root 3 over 2. It looks very similar to what we did in the focus, except this one has an I in front of the square root. And that's what I want you to keep in mind as you're doing this. It's still that same process that we worked with. We're now just getting a different type of answer out of the quadratic formula. Now, you do want to factor these things because they all have a 2 in common. So this should be written as negative 1 plus or minus I root 3, and it's over 1. Do you need the fraction anymore? So that is negative 1 plus or minus I root 3. And how many zeros is that? Because these are x equals. That's 2 of them. One of them is x equals negative 1 plus I root 3. And the other one is negative 1 minus I root 3. So we still get 2 really nasty looking conclusions there. They have I in them, they have square roots. They're not very pretty to work with, but they are roots of this polynomial. And multiplying it out would make them all work. So if we come back to where I have it all typed, that's where I get that. Similarly, I do the same thing over here. And I end up down with that. It's still the quadratic formula. I still get a negative up here, but you notice the difference between these. This one is, the one in front of this is negative, the one here is positive. So if we list out all of these roots, this is what I ended up with. And what I want to do is I want to write this thing in factored form. So let's practice that. This works just like it has before. Each one of these things needs to be solved for 0. So we get an x equals 2, x equals -2, x equals -1, and we're going to leave the plus or minus in here for right now. Make it a little bit less writing for us, okay? And each one of these needs to be solved for 0 to figure out what was in the parentheses when we started in the factored form. So this is x minus 2 equals 0. So the first parenthesis should be x minus 2. This one is x plus 2 equals 0. So our second, does it matter what order I list the stuff in these parentheses? Like, could I have written it like this, x plus 2, then x minus 2? Is that the same thing? That is the same thing. So don't get hung up on which one you do first, which one you do second, third, and so on and so forth. It just make sure you get them all in there, lay it out. Now let's work with this one. We're going to add the 1 to the other side. And what happens is, I'm not going to write 2 equations here. I'm going to kind of cheat. That plus or minus symbol stays with it when it goes over here. Because if it's negative, when I have to add it. If it's positive, then I'll have to subtract it. It stays the same. But that means that I get 2 things inside the parentheses here. I'm going to get x plus 1 plus I root 3. Then I'm going to get x plus 1 minus I root 3. I'm going to solve this one for 0, minus 1. And because of that plus or minus symbol, it just kind of goes with it. So this is in there, and we just got to separate the plus or minus now. It's minus 1 plus I root 3. And x minus 1 minus I root 3. All different combinations are in there. This is the factored form with the complex zeros listed of that polynomial. If you drew the boxes and multiplied it back out, guess where you would end up? You'd end up with x to the 6 minus 64 if you multiplied everything out, because things would cancel. No, we're not going to do it this afternoon, especially not one with the square roots yet. Okay, but I'll show you one eventually that will get us there. So this factoring, it continues forward, okay? And what we're really getting to here is we're getting to the conclusion that every single polynomial will always be able to be factored down completely into linear factors or binomials, and that the number of binomials you'll have will always match the degree. And that also means if we look at the graph, like this was x to the 6 minus 64. So let's look at the graph. X to the 6th minus 64. Looks like a parabola because it's even powered, both ends point up, but it doesn't have, we can see right away, does it have 6 roots like it should? Now we only see 2, but we know at this point it should have 6. So that tells me right off the bat is if I only see 2 and it should have 6, the other 4 are complex. They're the ones that we don't see crossing the x-axis. and I don't have a really good one, another one off the top of my head to show you this process. There's some in the work, but I suggest get used to graphing them and looking, okay? Because it also gives you a good starting point. If it's a third power function and it only hits once and you can see it, hey, you can use that 0 to get down to the quadratic and find the two complex solutions from there, okay? This first example I did was pretty tough because I tried to do the easy factoring, and sometimes that makes it a little bit tougher. But it's the same process. What we're doing now is we're just classifying that we can have this real specific type of answer of complex numbers as well, because we get down to our quadratics.